This is VLSC updates. Hope you all are doing well. This is the continuation of static timing analysis session. Last session we saw basics of static timing analysis and what is setup time, what is hold time, what are the different timing paths are involved. I'm just showing my screen. If you see here, we saw that. So we have covered these basics, like what are the different timing parameters for the combination and the sequential block. This is the combinational block. We have this propagation delay, and for the sequential block, we have this setup time and the hold time parameters. Along with that, we have the clock to queue delay, which are the important parameters, and this might vary based on the standard cells. And then we saw that what is setup time and what is hold time. As we all are aware, setup time is a time in which the data should be stable for the proper sampling before the active clock edge, and the hold time is the timing. So after the clock edge, the data must be stable for the defined time, which is called the hold time. So this is the which happens with the clock edge. Yeah. And then we saw the different timing paths. The primary path is like only the pure combinational logic with the input to output, which is called input to output path. And then we have this path which is input registered path. So there is external input which is coming to the chip, and so we are just calculating the input to this registered path here. We need to meet the proper timing for this path also, and we have this register to registered path, which is in the design itself. It's not the external chip. This is in the design. We will have the multiple logics between register to registers. So we need to calculate the timings between the register to register path, and basically we can categorize in 4 types, right? So one is from the external chip to the input register, and the internal register to register. We have multiple modules. Okay, data has to be traversed between the modules. So those things will happen between the registers, and register to output. We need to communicate to the external world. So register to output path, we need to make sure we are properly sending the valid data. So how are we making sure these paths are properly met and the timings are met for this path? With the help of constraints. Okay, we'll see the constraints in a separate session. What are the different categories of constraints involved and how they are playing the important role in that. Okay. So after that we saw, this is the overall thing. What is the data path and the clock path? So data path is something where data will be traversed from one register to the other register, and the clock path is separate, where the clock will be connected from one flop to other flops, which will be coming from the separate path. So in generally in any design, in FPGA, so we will have the separate path for the clock and the data, which is called the clock tree. We have the clock tree in FPGA, in ASIC also. Okay, so the data has to be separate and the clock has to be separate. If suppose if we are putting the data into the clock path, then it will create a lot of congestion, and in that case we need to make sure like we are properly routing the data and the clock separately. So this is overall summary of the different timing paths, like input to output, and input register, register to register, and register to output path. Okay. So this is the session we saw the last time, and in this session just wanted to cover a little bit more with the calculations, like how do we calculate setup and hold slab, what are different parameters are required. I wanted to cover 2 different scenario. So after that I want to mention the different kind of the constraints categories, and we will go on with that. So here, so this is called launch flop, this is called capture flop. Okay, So the data will be launched from here and it will get captured in this flop, and there is a combo logic. This is a random logic. Okay, so there are two main timing calculations involved in this. One is the arrival time, the other one is the required time. The arrival time we calculate in the data path. This is the data path from clock to data arrives at this registered place. Okay, and the record time is something like the clock to clock here in this flop to this flop, launch flop to capture flop. So let us remind these terminologies like launch flop and the capture flop, and we have the arrival time and the required time. Okay, so in the clock I just mentioned launch edge and the capture edge. Okay, so here the timing parameters I mentioned as clock to Q delay is 2 nanoseconds, and the propagation delay is 4 nanoseconds for the combo logic, and again the clock to Q delay here is 2 nanoseconds, and we have the setup and hold timing parameters here. I am taking for 1 nanoseconds and the 2 nanoseconds here. Okay, so for the arrival time, this is the equation I just mentioned here. So if you have any, the arrival time is something like from here. Let me just highlight that. So it should come from the clock. When the clock arrives at this flop, and when the data arrives at this place, and data arrives at this place, the whole path is called arrival time. Suppose if you have any buffer here, the clock is taking a nanoseconds to reach out to this, clock, the clock port of this flop. Okay, there is a delay. We need to include that delay also. In this case, I'm just assuming the ideal clock delay here. The clock arrives at 0 nanoseconds at this port. So once the clock arrives, we have the clock to Q nanosecond, clock to Q delay, which is 2 nanoseconds, and we have the propagation delay, which is 4 nanoseconds, and we have the setup time of this flop, which is 1 nanosecond. Okay, so totally, if you calculate, my arrival time is 2 nanoseconds plus 4 nanoseconds plus 1 nanoseconds. It's a 7 nanoseconds, right? Let me just put the number here. Which means my data arrives at 7 nanoseconds at this capture flop. Okay, so in the required time, this is the calculation for the required time. This is T means clock period in nanoseconds, and we had a setup time. Okay, so in this case I took that the clock period is 10 nanoseconds here. Okay, let me mention that this is 10 nanoseconds in this case, and we know the setup time there. Okay, setup time is 1 nanoseconds in our case. The required time is 9 nanoseconds totally, right? Let me mention this. Which means the data should arrive before 9 nanoseconds. That's the idea. The data should arrive before 9 nanoseconds. If the data arrives before 9 nanoseconds, so we can get the proper data captured. So in this case it is possible, right? Because the arrival time is 7 nanoseconds, but we have the record time is 9 nanoseconds. Data arrives 2 nanoseconds before the expected time. Let's say like the data arrives at here itself. Let's say I'm just putting it here as a 7 nanoseconds. Just so we are in the safer side. Okay, so data arrives earlier than expected, earlier than the required time. So we are in the safer side here. The data arrives at this time. Let me put this. Okay, so the arrival time is 7 nanoseconds here. We are ahead. Arrival time is 7 nanoseconds here. So we are ahead. The data is arriving earlier than expected. Okay, this is one thing. So in this case, we don't see any slack and all. So generally, the setup slack will be done in the next clock cycle, in the next clock edge. Okay, this is the launch edge. The data is being launched at this edge, and the data is being captured at this edge. So we need to make sure the data arrives within this clock period. Okay, so we need to make sure we have the proper combo delay and all. If suppose you have the more combo delay, you need to work it out in this case. One thing, like let's say if you have the combo delay of 6 or 7 nanoseconds, what happens here? So 3 nanoseconds will be adding the delay. So the arrival time will goes on 10 nanoseconds. So there will be a set of slack in that case. One thing, you need to break this combo logic. We will see, we saw an example design also for that. We need to break this combo logic, or we need to just increase the clock period. There is only two options here. Okay, just increase the clock period to 11 nanoseconds or 12 nanoseconds. But in that case, you're not going to meet your timing requirement. Suppose if you want to close it in the 10, here you can reduce the time also here. We have the opportunity to reduce the clock period to 7 nanoseconds here. Okay, which means our design is going to run a little bit faster than expected here. So on the other hand, the whole slack is something like we have the whole time is 2 nanoseconds. Once the data arrived at this clock edge, the whole slack will be done at the same clock edge, not in the different clock edge. Okay, so let's say the data arrived. So what happens? This flop will start processing the next data. Okay, in the same clock edge, this will start processing the next data. At the same time, the previous data is being processed at the capture flop. Okay, let's say we have the here it will take some time to reach out to this capture flop, right? So in the same clock edge, the next data is being processed here. It will take 2 nanoseconds plus 4 nanoseconds, and then it will reach out to this place, this flop here. So we have the whole time of 2 nanoseconds. So the previous data will get sampled quickly. So we have the window of like 4 nanoseconds here. Okay, which means it is getting delayed. Okay, so the previous data will get sampled without any issues, without any slack, without any whole slack in this case. Okay, so this is one thing, and so in this case there is no setup slack, there is no whole slack also. So in the second case, I just wanted to reduce the the combinational path delay. Here we have the combinational path delay of 1 nanoseconds and the 2 nanoseconds here. So just calculate what is our arrival time here. Arrival time is something like 2 nanoseconds plus 1 nanoseconds, which is like 3 nanoseconds plus 1 setup time, 1 nanosecond. Total is 4 nanoseconds here. Let me mention that. Totally we have the 4 nanoseconds. We are much ahead. Okay, so the 4 nanoseconds will come somewhere here. Let me put that line. We are much ahead here, right? So my data arrives at this place itself. Actual record period is something like we have the 10 nanoseconds minus 1 nanoseconds. It's 9 nanoseconds, but our data is arriving 5 nanoseconds before expected. So we are in safer place for the setup slack. What about the whole slack? Once the data is processed, we have the whole slack of 4 nanoseconds. Let's say this is 4 nanoseconds. So the data should be stable in this window for 4 nanoseconds. Will it be? It won't, because we have the low combo path delay here. Okay, so once the data captured in this capture flop, in the same clock edge, it will start processing the new data here. So the new data will arrive at 2 nanoseconds plus 1 nanoseconds. At 3 nanoseconds, the new data will arrive here, but the previous data was not sampled yet. The previous data is still being processed, because the whole time it should be is 4 nanoseconds. Okay, in this window we have the 4 nanoseconds of whole timing, but this is the previous data. Let me put the previous data is 4 nanoseconds, but the current data arrives at 3 nanoseconds due to there is less combo path delay there. Okay, but the previous data has to be there for minimum 4 nanoseconds. But due to this combo path delay is very low, the data arrives at earlier. Okay, so in this case there is a whole slack because the previous data is not getting validated properly, and the current data also is not going to be sampled properly. Okay, so we have the problem here. So how do we fix this problem? One thing, we need to increase the combo path delay, or we have to pick the standard cell which has less hold time, which is which is not it is possible, but it depends on the standard cell we are using it. But generally we can this is already given by the manufacturer. Okay, I mean the tool manufacturer itself, we cannot go and change this, right, in the design. One thing is like we can change this combo path delay, we can increase the combo path delay, we can add some buffer for 1 or 2 nanoseconds and increase this combo path delay to meet this whole timing path. This is another way we can do this. Okay, so this is the other scenario here. And yeah, so I just wanted to show the different timing constraints category, which we will be covering in detail in the next session. Okay, there are 4 categories of the timing constraints. And the first one is the clock constraints, like we have the create clock and create generated clock, and other parameters like jitter and the uncertainty and the delay, which is associated with the clock. And we have the delay, input delay and output delay, and we have the clock groups and the false path. What if we have multiple clock domains, and what if we have the the false path means like asynchronous paths, and some paths in a design which is which is never going to be realized. Okay, and we need to identify those paths, we need to define them as a false path. And we have the multi-cycle path, and in some cases the data will not arrive in the same in one clock cycle. So in that case, suppose we have the bigger combinational logic, so the data might take 2 to 3 clock cycles in that case. So we need to define them as a multi-cycle path and all. Okay, so these are the different timing constraints category, which we will be covering in detail. How do we write each constraints, and how it impacts design parameters. Okay, so along with that, I just wanted to show you, last time we took one design. Okay, and I was mentioning in one of my posts in the LinkedIn. I hope you are all following that. I have this constraint file. I was expecting this design to close at 5 nanoseconds. I think it's closing. Looks like, yeah, I have this every slack is positive here. Okay, there is no negative slack in this design, but still I can reduce this time and see whether it is creating any timing issues here. Okay, and the RTL which we had is I have a schematic, I believe. Yeah, we have to do this combinational multiplication. So in the older design, we do not have these registers. We will do all the combinational multiplication in this between these 2 registers. Okay, and in that case, like sometimes we might not meet the timing requirement. So I just thought of breaking that combo path and adding 2 registers here. So it will do the pipelining things. Okay, I'm just storing the intermediate results and then do the final multiplication. Initial the latency might be 1 clock cycle delayed, but this is the efficient way to do. It will increase our clock period also, and also it will add more give the efficient optimized resource. If you see the resource consumption here, it would be like different from in an improved way. We have the DSP slides, and we have the flops and the LUTs here. Okay, so still we can try to break down this logic. I can show you the RTL here. I just break that combinational multiplication operation and added the registers over there. Instead of doing it in the single statement, I just break down this statement. Still we can break down this statement, like we can do this operation separately, and we can do this operation separately. Okay, and then we can put it in one more register. We can add a register in this place also. Okay, here also we can add on registers, add the registers, and then we can do this operation and then store it in the register and then do this operation and then go to this register. The initial latency might be like 2 to 3 clock cycle delay, but after that you will get you will get the results continuously. Okay, but in this case we can increase the timing between the registers. That's the only advantage here. And yeah, I would recommend you to try that option also. At the same time, you need to make sure the functional wise it is not broken at all. While breaking the logic, we should make sure the functionality is not broken. It is the one thing we need to keep in mind. Okay, so yeah, I hope you can try this out, and you can comment out in this video session below that if you have any different scenario in mind, if you have any questions, and we can discuss in detail. Okay, and yeah, please comment out on any questions. We'll see it in next session in detail on this topic. Okay, hope this helps, and thank you all. Thanks for your time. Yeah, bye.